Thanks, Kevin. Have a good weekend.
Thanks, Dr.
Thanks, Eddie. Have a good weekend.
I visited Max's office. We're doing a beautiful. Still got to work on 417.
See you, Chris. Hey.
So back to the graph, in order to be stable, it just depends on the finite difference, right? If it doesn't have observations.
Right. Yeah.
Okay.
Yeah. So those. Yeah. Go ahead.
I was noticing like it was drawn like to the left.
Yeah.
And from the Matlab, it was like to the right of the exact. Does that also contribute to being stable, or?
Yeah. So the instability is just the oscillations. And so if you see it kind of flopping up and down like that, that instability. If it's to the left or to the right, that's just an accuracy.
Oh, okay.
And so the only way to fix accuracy is to just refine the grids.
Okay.
Yeah. So that's kind of the solution to everything, is just to refine your grid. But there's kind of some nuance to it in terms of how that affects stability and accuracy. Yep. Yep. Have a good weekend. Not yet. So I'll probably grade them on Friday, and then after I grade them, then I'll post the solutions.
Okay.
They finally messaged me about my after-hours pass
Oh, yeah?
today.
Oh,
Really fucked me.
yeah, it's, yeah, I mean, to peel back the curtain a little bit, things are really backed up.
Yeah.
We've had a lot of, we've had a lot of admin assistants that are either, you know, got promoted or they moved on to another position. And so we're pretty short-staffed in the department right now. Yeah, it's hard because I'm doing a lot of stuff with my research right now, and I'm having to pay for a lot of stuff out of pocket just because it takes them just so long to process stuff. I just want to buy these two like $16 dongles from Amazon, and I know it's going to take them like a month to process it, so I just bought it myself. And I'm gonna. They're not going to reimburse me.
Really?
I'm just going to take the hit, but that's
Oh my lord.
that's how it is now. But you know. But they're doing their best. I mean, we have two people on halftime right now, and like I know they're really swamped. And so, you know, for this is it's pretty small, and so it's just $16, and so I didn't mind it. But yeah, for the bigger things, it takes a long time for them to process. Okay, it's 7 o'clock, so let's go ahead and get started. All right, good evening, everyone. How's everyone doing today? Everyone have a good long weekend? Yeah, catching up on work probably. That's probably what we all spent the day doing. But you know, that's kind of how it is. Okay, and so today, so I'm going to be skipping ahead a little bit just to kind of make sure we're still on schedule. So there's kind of a second half of the beam equations and notes that has to do with distributed loading, and so I'm going to skip over most of it. And so there's one small part I want to cover, but I did want to get onto frame equations because what my hope is by next Wednesday we'll actually start working with Matlab, and so I want to make sure we keep that date. And more importantly, I want to make sure that we're on schedule for the midterm as well. Okay. And so speaking of the midterm, we're going to have a midterm in this class. It's going to be on Wednesday, March 9th. And so that's 2 weeks from now. Okay. And so I want to give you the heads up now, just so you can start preparing for it. And so just like we talked about at the beginning of the semester, the exam is going to take place in person. And so please plan to be here on Wednesday, March 9th. Because there's no plans for any arrangements to take it virtually as at this time. Okay. In terms of what you can bring for the exam, you can bring a single 8.5 by 11 sheet of notes. You can use both sides, and so you can write on both sides of the sheet of notes. And you can write it, you can print it. It doesn't really matter to me. It's just it's your sheet of notes. Okay. The only requirement that I have for your sheet of notes is just that that you can read it with your eyes. And so I don't want people bringing in like magnifying glasses or like I know people do that thing with like they print partially in red and they print on top of it with blue, and you can use special vision to like look at one or the other. None of that stuff. You have to be able to read it with your eyes. Okay. But besides that, you can put anything that you want on there. The reason I do the sheet of notes is, I think, you guys are grad students, and so I think you guys are beyond the point where, you guys need to memorize stuff. And so, especially with this class, because there's a lot of, element stiffness matrices there are a lot of terms that are involved. And so, you shouldn't have to memorize those things. And so that's part of the reason why I give you the sheet of notes. But the other reason is I find that it's always a great study tool as well, because we've covered a lot of content up to this point. Even up to today, we've covered a ton of stuff. And so if you take all what we learned and just kind of read through everything, and if you're going to try to condense that into a single sheet of notes, your brain kind of already intuitively kind of goes through this process of condensing, what's the most important things that we've learned so far, and put that onto the sheet of notes, right? And so that takes a while. And so, ideally, the sheet of notes should take up, a good chunk of your study time. But that itself is already great study. And so, I have this to kind of help you out with that, because I've seen kind of both extremes. And so I've seen the sheet of notes where people, take the time, go through their notes, write them what they think are the most important highlights, organize it really well, color code it, and those students do really well. The other extreme that I've seen is that people just take the posted lecture notes or the posted homework solutions and just screenshot everything and just print it really, really small on the sheet of notes, so that they have everything available to them. So that for them, it's essentially like an open note exam. And almost universally, those people do not do well on the exam, because they spend more time trying to look for the certain information on their sheet of notes, going like this, doing like the Parks and Rec, Mr. Chang thing. Yeah. Than they do for the exam. And for this class in particular, that's going to be really harmful, because you guys probably noticed already from the homeworks that these problems are really time consuming. And so you want to spend as much time writing and working on the problems as you can, rather than looking stuff up. Okay. And so I really recommend that you guys, really, don't just, copy stuff from the notes, or like screenshot the notes and put it on your cheat sheet. Actually go through and condense everything, because you're going to need the time to actually write stuff down, because this, this content just by nature is very, very time consuming. Okay. So the other thing, question.
So I'm assuming there won't be, you won't give out the equations or whatever.
No. Yeah. So you'll be responsible for writing the equations yourself. So I'm just going to give you the problems. So something else I'm going to give you is I'm going to give you a study guide. And so early next week, you can expect the study guide to be posted on Canvas. That will kind of help you kind of condense all the material already. But it'll basically just be our list of learning objectives that we have each day. But I think having that list and having it all in one sheet, I think will usually helps people study. And so you can expect that early next week. And one thing that I've been doing recently, starting with the virtual instruction, is recording a review video. So unfortunately, there's not enough time to do review in the class, just because we cover so much content. But I do want to give you a video that kind of help you review stuff. So next Friday, what I plan to do is I plan to record a video for you that reviews kind of some of the most important topics. Okay. And you can expect that video to be about an hour long. So it's like kind of like an extra lecture. But even within that video, there's not enough time to cover absolutely everything that there is to know on the exam. And so next week, I'm going to put out a poll on Canvas for you to vote on what you think are probably the most 1 or 2 topics that you feel most uncomfortable with. And I'm going to focus on the topics that people tend to vote on the most. So probably the top 2 topics I'm going to cover in the review video. Okay. Question.
Format would be midterm going to look like?
Yeah, good question. So the format of the exam is going to be there will be 4 short answer questions. Okay. So these will be worth 40% of the points. Okay. there'll be one truss problem, one beam problem. Okay. And I do have one more problem planned, but I haven't tested it yet. I don't know if it's feasible in a single exam session. But it's going to be one frame problem, and we'll go over frames today, and you'll see why that I don't think it might not be feasible, or maybe I'll make it really simple and I'll just make it really short as well. Okay, and so these combined together will be 60% of the points. Okay, right. And so in terms of what you're expected to do, you're not going to have MATLAB available for you on the exam, and so I'm not going to expect you to solve a problem fully. But what I do expect you to do is to write out all the element stiffness matrices for all the elements. And I'll make the numbers easy, so you're not going to spend a lot of time punching numbers in your calculator. And then I'm going to expect you to assemble that into a single linear system and apply boundary conditions. Okay, so basically all the steps of the finite element process up until solve. Okay, and so your final solutions are going to be therefore kind of your final global linear systems with the boundary conditions applied to. Question?
Can we expect like combination of like beam spring type of problems? Like
Yep, you could. Yep. And so I might mix and match these things as well. But that's kind of the rough breakdown of what I'm thinking. I haven't written the exam yet, but that's kind of what I'm thinking of it at this point.
The dilemma. I haven't written the exam yet.
I mean, it's true.
I have friends that tell me that like 24 hours before an exam.
Well, 24 hours, they might be mine, but they might not be. I don't know. But this is 2 weeks ahead, so I definitely haven't written the exam yet. I didn't even think about it until like 20 minutes before the class today. But I did remember. So I did want to give you a heads up, before, just because it's 2 weeks out.
The ANSYS stuff you cover?
No. So the answer stuff will not be on the exam.
So like 4 short answers.
Yeah.
Will that kind of be like biomechanics last semester? where
Exactly.
you're just like asking conceptual type questions?
Right. Yeah. So the short answer questions are going to be conceptual questions. And so I imagine that you can answer those in maybe like 2 or 3 or 4 sentences each.
What would that look like?
It would be something conceptual. So like, on the last homework, the first problem, I have the short answer question. It would be kind of in the same style as that. Yeah. So maybe it would be like something like, I don't know. Describe to me how a beam deforms compared to a truss. Yeah. So you can draw a picture, you can write sentences or things like that. Yeah. Mm-hmm. Okay, any other questions on the exam format before we start the lecture today? Okay, so I did want to make you guys aware of it. It's because next week I'm going to start putting out some content for the exam. So the study guide will come out next week, and the review video will be next Friday as well. Okay. And the next homework is posted already as well. And so that next homework that's out right now, that's going to be covered on the exam. And since that one's going to be due a little bit close to the exam, I think I have it due next Friday. I have to double check on that. That one I'm going to post the solutions basically right after that's due, so that you'll have those available for you to help you study. Yeah, usually I don't post solutions until after I grade stuff, but since that one's cutting it a little bit close to the exam, I'll post the solutions probably a day after it's due.
I almost do the Monday before. Right?
The Monday exam. Okay. Yeah, I didn't remember the exact due date, but yeah, I'll post the solutions for that right before. Yeah, right after it's due. Okay, all right, and so that's the exam. And so let's go ahead and continue on where we left off. And so last time we were talking about beam equations. Right, and so last time we went over the kind of the concept of what a beam is, right? Because remember, a beam is a structure that looks like this. It's long and slender, just like our trusses, but instead of deforming axially, instead of compression and extension, what we have instead are transverse displacements. And we also have rotations. Okay. 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 And so last time we went over, how to solve beam problems. So we looked at the element stiffness matrices for beams, and we saw how those fit in together, and all this stuff. And so kind of the upshot for the beam equations thing is that, it's the same process that we have been doing for all of our direct stiffness problems. It's just that the element stiffness matrix for a beam is different. Okay, but you follow the exact same process as before. And so if you look at the end of the beam set of lecture notes, there's actually, a big section left called distributed loading. Okay. And so that has to do with situations where a load is not applied at a point, but instead is distributed over a period of over a certain space. And so I'm going to skip a lot of that just to kind of make sure we're still on schedule. Just because that's kind of a big tedious part of the work anyway. And so instead I want to jump into frame equations. Okay. Question. So is it impossible for a beam to have axial displacement? And so it seems like beam elements are capable of axial displacement. And so the assumption for beams is that they don't have any axial displacement. But what we're going to go over today are frame elements. And so frame elements can do everything. So frame elements can have axial displacement, it can have transverse displacement, and it can have rotations as well. And so if you have a beam element that has axial displacements, we call those frames typically. And then the biggest difference is that your element stiffness matrix has to be able to reflect that. Yeah. All right. And so that's kind of where we're going today. But before we get there, I did want to talk about one important topic that's kind of embedded within the distributed loading. Well, it's kind of a good lead into what we're going to do after the midterm anyway. And that has to do with the concept of what's called an interpolation function. All right. And so, throughout this entire unit, we've been solving these finite element problems. But if you notice, we have one, really kind of glaring kind of limitation to our problems, right? And that limitation is that, we're kind of limited in that we can only solve for the solutions at the nodes of our system, okay? And so that's kind of glaring, right? Because what if we wanted to find out, what is the displacement right here in the middle of the beam, right? And sometimes that's of interest, right? And so sometimes we want to find that out. Right now we have no way to solve for that. Okay? And so the purpose of an interpolation function is to take those nodal solutions and then interpolate them. Interpolate them to other parts of your element. Okay. Okay. And so the idea of an interpolation function is not unique to direct stiffness. And so this idea is going to come back, once we go over more general finite elements in the second half of the course. Okay. but it's useful to talk about here. And so for a beam element, one candidate for an interpolation function is a cubic polynomial. Okay. And so let's say that we're interested in a function uy of x. Okay. And so the most generic cubic polynomial looks like the following. Okay. Okay. And so we have our constant term a0, we have our linear term a1x, we have a quadratic term a2x squared, and we have a cubic term a3x cubed. Okay. And so the reason I called it a candidate is that the interpolation function can be almost anything. Okay. So I chose a cubic one for this case because it's you'll see very soon. But once we get to kind of more general finite elements, the interpolation function that we choose is most of the time going to be either a linear polynomial or a quadratic polynomial. Okay. And so if you remember from our ANSYS activity, one of the settings that we chose for elements was the element order. And so one of the element orders, we either chose it to be linear or quadratic. And so what that refers to specifically is the order of the interpolation function. And so we'll get into that more later, but I just kind of want to introduce the idea right now. Okay. Right. And so when you have a generic polynomial like this, the goal is to solve for what these coefficients are. Okay. And the way that we typically solve for these is we enforce, or we specify what are called nodal conditions. And what those nodal conditions are just to ensure that this function here matches up the nodal solutions at our nodes. Okay. Because even though the point of the interpolation function is to interpolate, in between the nodes, they still have to match the nodal solutions. And so for our beam, if we assume that this beam here varies from x is equal to 0, and we say the right side of the beam is x is equal to L, okay? And so the nodal conditions for our beam look like the following, okay? And so if we plug in x is equal to 0, then of course, then the uy has to equal to u1y, okay? Right, and if we plug in x is equal to L, then our solution must equal u2y, right? And so that's just straight up the nodal solutions for our functions. Right? Right. And so the other two nodal conditions, or the other two conditions that we have at our nodes, have to do with the fact that we know the rotations at the nodes as well. Okay. Okay, so theta 1, theta 2 have to be in here somehow. Okay. But the question is, how do we actually relate this to the transverse displacements of our nodes? Okay. Okay. It turns out the rotations are related to the derivative of the transverse displacements. right? And so if you take the derivative of our uy function with respect to x, and you set x is equal to 0, then that should give you theta 1. And if you take the derivative of uy with respect to x, and set x equal to L, then you should get theta 2. Okay. And so these 4 conditions are going to be enough to solve for our 4 coefficients here. Okay.
Considered boundary conditions.
Yeah, you can consider them. You can consider them boundary conditions if your boundary is just a single element like this. But I'm using the term nodal conditions because they're different from the boundary conditions on the entire system. Because right now we're just looking at a single element. Yeah. But mathematically they function exactly the same as boundary conditions. Exactly. Yeah. Mhm. Okay. And so unfortunately it's quite a bit of math, and so it would take probably the greater part of this lecture to actually run through the math of solving this. And so I'm just going to give you the solution. Okay. And so the solution for this is uy of x is equal to 2 divided by L cubed. Okay. Plus all of that is the coefficient for x cubed, and so that's the A3 term. Okay. So that's the x squared term. Thankfully, the last 2 terms are much more reasonable. Okay. And so that's what you get for the interpolation function for a beam. Okay. So it's kind of a monster. It's not a pretty function at all. Okay. But that's mostly just because the beam is a little bit complex. Okay. Yeah.
I know this is a homework question to solve this thing, but I'm not exactly sure what are we solving for.
Yeah. So that I'm gonna go over that in a second. And the reason I'm kind of bringing this up is because it's a homework problem, and so I want to make sure that you guys are good with that. And so just to kind of repeat that, the reason I'm bringing this up is because it is a homework problem. Because one thing that we skipped here in this beam unit was we didn't really derive the beam element stiffness matrix. And so if you looked at the latest homework, one of the short answer questions is asking you to derive that beam element stiffness matrix. Okay. And so the way you do that is you basically use this function here. Okay. Okay. Right, and so to derive the beam element stiffness matrix, you're going to take this interpolation function and you're going to plug it into the beam equations. Okay. And so the first beam equation is m of x is equal to ei times b squared uy dx squared. Okay. And then fy of x is equal to ei d cubed uy dx cubed. Okay. And so if you take this expression above, we take our interpolation function and we plug it into these equations, what that's going to give you is basically all the different rows of the element stiffness matrix for a beam. Okay. And so, for example, let's I'm not going to go through the whole math, but I'll talk you through kind of the first line of the beam element stiffness matrix. Okay. And so to get the first line of the beam element stiffness matrix, we're going to take this expression here. Okay. This uy of x. I'm going to take 3 derivatives of this. Which is pretty nice because, if we're taking 3 derivatives, then of course the constant term is going to go away. This term is also going to go away, right? And so we take a derivative of a constant times x. You take it twice, it's going to go away. Yep. And then for the 3rd time, then the x squared term is going to go away as well. Okay. And then all you're going to be left with is this term right here multiplied by 6. Because you get 6 that comes as a derivative of x cubed, right? And so if you evaluate that term and you multiply the whole thing by EI, and you can factor out L cubed as well, what you'll see is that that'll give you exactly the first line of the beam element stiffness matrix. Okay. Right. And so you're going to do that, for the first line. The second line is going to be for this equation right here. Okay. So you're going to plug it in for this one. But for this one, you only take 2 derivatives. Okay. 3rd line, you plug into this one as well. And then 4th line, you plug it into that one. Okay. And you evaluate it at either x equal to 0 or x is equal to L. And that'll give you each line of the element stiffness matrix. Okay. Of course, you're going to have to do some algebra and factor out each term specifically. You're going to have a u1y, u2y, theta 1, theta 2 term. But that's basically how you should approach that problem. Okay, any questions on that before we move on to frames? Yeah. Yeah.
So that first line, you're basically gonna so you factor out the L squared, then you have an L left where the L squared is, and then you just multiply through, so you get 12u1 minus 12u2.
Yep.
Plus, and then you just take it all the way from there.
Yep.
Basically build it.
Yep. And if you look at the coefficients in front of each of the u's and the thetas, you'll see that those are exactly the entries in the beam element stiffness matrix. Yeah. Okay. All right. Any other questions on this before we move on to frames? It's like an angle. Try and put it back in the flow system. You will have to change. Yeah. So we're going to talk about that today. So right now, we've only covered beams that are just hanging out horizontally, but of course you can have beams that are angled as well, and so you're gonna have to make adjustments on that based on the angle. But it will get pretty nasty. I will say it's not the most fun thing. So that's why I kind of waited until we do frames to do that. Okay, all right. So let's go ahead and move on to frames. Okay. All right, so actually going back to a question that Tristan asked at the beginning, it's definitely possible to have structural elements that do axial deformation, transverse deformation, and rotations all at the same time. Okay, and so the types of elements that can capture all of these things together are known as frame elements. Transverse And so frame elements are kind of the most unique, or not the most unique, the most flexible element type, because it accounts for all forms of deformation. Okay. And so visually it looks something like this. And so, we have a frame element that looks like this. Okay. Of course, we're going to have our axial deformations. And so I'm bringing the hats back because remember, these are going to be displacements within the local coordinates of the element itself. Okay. You have U1 y hat and U2 y hat. Okay. And you also have theta 1 and theta 2. So those don't get a hat just because those are dimensionless. And so whether you're rotated up or down, the rotations have the same the same capabilities. Okay. Okay. And so in some sense, you can argue that frames are kind of the only elements that are out there, compared to trusses and beams, because any stick or any kind of slender element, it doesn't know if it's a truss or a beam, and so it's going to just deform how it's going to deform. And so if you want kind of the most flexible form of the structural elements, frames are the way to go. But you'll see very quickly why people like to avoid using these, because they require kind of an inordinate amount of work compared to trusses and beams. If you can even believe it, because even the truss and beam problems that we've looked at already, it's kind of already really tedious and amount of work. But frames kind of take it up to the next level, just because it can account for all these different kinds of deformations. Okay. And so today, I think what we'll have time for today is we'll cover the frame element stiffness matrix, how we can derive that, and we might be able to start an example problem, okay? And then we'll probably finish up everything on Monday. Okay, any questions on this so far? Okay. All right, and so before we do that, let's kind of address kind of the elephant in the room. And so let's go back to beams, and let's see how we can adjust our beam equations for any kind of rotations. Okay. Okay. All right, so recall, when we were talking about, rotation of truss elements, we had what we called our transformation matrix. Okay. Right, and so if we were to transform from the local coordinates, okay, and we wanted to transform these into the stationary coordinates, remember the stationary coordinates, you can think of them as like the reference coordinates, and so that's kind of the usual x and y, the horizontal x and the vertical y. Okay. What we had to do was we had to multiply by this, by this combination of sines and cosines. Okay. Where c is cosine of theta. Since we're using theta for rotations, let me use a different symbol here. So c will be cosine of phi, and sine, and s will be sine of phi. Okay. Where phi, remember, is the amount that our element is rotated. Okay. Okay. So remember, that's different than our nodal rotational displacements. Okay, so this refers to, let's say that our element looks like this, right? Then this angle right here is phi. Okay. And so phi here is, I should say, this is a an element orientation angle. Okay, so let's apply this transformation matrix to our beam elements. Okay. And so it looks something like this. Okay. And so in the local coordinates, we only have remember, local to a beam element, we only have transverse displacements and we only have rotations, okay? But in the stationary coordinates, we have to account for both x and y displacements, okay? Right, and so in the stationary coordinates, because even if our beam here is displacing like that, if we put that in terms of the stationary coordinates, that can have x and y components. Okay, so I'm doing this a little bit differently than our trusses in that I'm having kind of a lopsided transformation matrix, and so transformation matrix here is going to be 4 by 6. Okay. Right, and so what you'll notice here is that because we're only dealing with u1 y hat, I've only taken just the last row of that transformation matrix and I put it right here. Okay, and so since we don't have a local x deformation, then there's no need for that first row. So that's why I've this is kind of a truncated version of this of that transformation matrix. I had a brain fart. I couldn't think of the word truncated for a while. Okay. Any questions on this? Okay. All right. And so I'll skip a lot of the algebra that we did last time. And so, if you remember from last time, our result was that in order to get our element stiffness matrix in the stationary coordinates, okay, what we had to do was we took this matrix right here. Okay, if we call this matrix our T matrix, okay, and so if we took our element stiffness matrix in the local system, okay, remember the result that we got from last time is that if we post multiplied by our transformation matrix, okay, and then we pre-multiplied by our our same transformation matrix, what this gets us is K, which is our stationary element stiffness. Okay. And so that's all I'm going to do. So I'm going to take the local element stiffness matrix for a beam, which is what we covered, last week. I'm going to pre-multiply it by the transpose of this matrix, and then I'm going to post-multiply by the matrix itself. Okay, and so if you work through the entire thing, you end up with a kind of a gargantuan 6x6 matrix. Okay. And so I might not have enough room, but I'll do my best here. Okay. Right, and so we end up with a 6x6 matrix, and so we have a EI over L cubed. Okay, so that's still there from our beam element stiffness. Okay, and then we end up with the following. Okay, and so we have 12 s squared minus 12 sc minus 6 times L times s. Okay, minus 12 s squared, 12 sc, and minus 6 L s. Okay, so let me go ahead and write out the rest of this. We have 12 c squared, 6 lc, 12 sc, minus 12 c squared, 6 lc. Okay. Where L, remember, is the length of the element. And just like I've done in the past, I'm only writing in the top half of the matrix because the other half is symmetric. Okay. Say again? Oh yeah, this is 4L squared right here. Yeah. So this right here, and I'll give you guys a minute or two to write it down. This is our element stiffness matrix for a beam. And the stationary coordinates. Okay. So we still have to add a few more terms in for the axial displacement as well. So, yeah. This is as big as it gets, and so it's still going to be 6x6. It's just we need to add some terms in there for the truss elements as well. Yeah. So we haven't. So what we're going to do is we're going to take the truss stuff and just add it to this. Okay. So yeah, it's a doozy. Yeah.
Third row, third column, 4L squared.
Yeah. This is 4L squared. I can make this a little bit nicer. As many elements as there is, and so if you have, we'll do an example with 4 nodes and 3 elements, I believe. And so I believe the global system for that one, let me see, is 1, 2, 3, 4, 5, 6, 7, 8, 9. Is the global system for that one is 12 by 12. Yeah. So that's why I don't think I'm going to put a frame problem on the exam, just because it's too crazy. It's Even on the homeworks, you guys will probably, my name will be part of a lot of profanity, I think, over the next week or so because of these frame problems. And but it's all set up. Okay, so these problems are meant to be kind of torture, because next Wednesday what we're going to do is we're going to learn how to implement this in MATLAB, and you'll see that MATLAB, it's in we'll probably spend 2 lectures doing it, and so we'll probably spend next Wednesday and and the following Monday talking about the MATLAB implementation. But MATLAB was designed for something like this. Okay? Because this is a lot, I know, but it's a lot of kind of repetitive calculations. And if there's one thing that MATLAB and computers are really good at, it's doing repetitive calculations and doing them with a lot of accuracy. All right, any other questions on this? Okay, all right, so that's just the beam stuff. And so in order to get frames, in order to get our element stiffness matrix or frames, we have to add in the axial displacement contributions as well. Okay, and so basically the way it works is that we basically just add in all the relevant truss stuff. Okay? And so if you remember, trusses don't have anything to do with angles. Okay, and so what you'll see is that when we add in the truss stuff, they only get added into certain chunks, and so they're going to get added into this chunk right here. Okay, because this has to do with u1x, u1y. Okay. It ignores this column completely. Okay, so we're not going to do anything there. And it ignores this row completely. Okay. And also ignores these rows completely as well. Okay, so it's going to be just here, here, and here. Okay. But the nice thing is that those systems are mostly decoupled. And so what we can do is we can just take our entries from our truss element stiffness matrix and just add them into the appropriate places. Okay. Okay, because you remember, the truss element stiffness matrix, it had u1x, u1y, and also has u2x, u2y, right? And so kind of in the same way that we apply when we do our assembly, whenever we have overlapping terms, we're just going to add them together. Okay. All right, and so let's go ahead and start. Oops. Just the M1. Okay. All right, and so let me go ahead and start writing out the element stiffness matrix for a frame. Okay. And so out in front right here, we have an E divided by L. Okay, so that's our new factor out in front. Okay. Okay, so I'll do this kind of entry by entry. Okay. So that's one term right there. One out of 36. Okay. That's the second term, 2 out of 36.
That's on
it's all in the notes. And so if you just want to look at it in the notes, then it's all there for you. Yeah, this is as close as it comes to torture. And so, you know, I'll go through it for you guys, but I've already gone through it, so you know, you guys don't have to. And of course, A here, capital A, remember that stands for the cross-sectional area. And so we haven't seen that in a while because that was only for truss elements. Okay. Okay. All right, so that's the entire first row of the matrix. Okay. Okay. All right, I'm gonna go ahead and continue, but you know, I'll zoom out for those of you who are writing it down as well. Okay. Well, let's go ahead and start working on the second row here. So the second row, we have AS squared plus 12I divided by L squared C squared. Oh, did I miss one? Hang on. Oh, I wrote this one twice. Sorry. Let me try this. There we go. Okay. Oops. Okay, so that's the second row. Okay. Move this over a little bit. This one over a little bit as well, just to make it line up a little better. Okay, now the third row. Third row is a lot easier, thankfully. We have 4I, 6I over LS minus 6I over LC, and then a 2I. Okay, so that's the third row. Okay. Right, 2 more rows. Okay. All right, and so that's the element stiffness matrix. Okay. Right. And of course, this is symmetric. Okay. And so this right here is the element stiffness matrix. 4 frames. All right. And so as I'm writing this, I'm thinking about, I'm thinking about what I assigned for you on the homeworks. And I think I'm going to make the very last problem optional. Because even for me, which knows these equations, that one took me about an hour just to kind of write everything down and to get everything in in Excel and everything. And so for you guys, I'm going to make that last one optional because it's kind of cruel. And so basically, if you haven't looked at the homework yet, the last problem on the homework is a bicycle frame. And so I think it has like 5 or 6 elements. And so you have to do this 5 or 6 times with different angles. And so it's kind of cruel. And so I'm going to make that very last one optional for you. Okay. All right. I'll send an email clarifying it after the class. Okay. All right. Any questions on this? Okay. All right, so we have 15 minutes left in class, and so I don't think we have time for the full example, but we can start it at least, okay? And I think we'll wrap it up. We'll get as far as we can, and then we'll wrap it up once that's 8:15. Okay. Okay. And so for this example, let's consider the following structure, which is composed of frame elements only. And you'll notice I picked the directions for these elements very deliberately to kind of save some space. Okay. All right, and so we have kind of this square looking thing. Okay. And so let's say that we have a horizontal force here of 10,000 pounds. Okay. And let's say that each length here, so this height right here is 10 feet. Okay. And this is also 10 feet. Okay. All right, so we have a perfect square basically. Okay, so we have 10 feet, 10 feet up, 10 feet across, and then 10 feet back down, with only a single one more force here. Okay, and so let's say that we have a moment here. And the moment here is equal to 5,000 pound inches. Okay. Okay. Next, let's list out the properties. Okay, and so let's say that we have a Young's modulus of 30 times 10 to the 6 psi. We also have a cross-sectional area of 10 inches square. Okay. And so these apply to all elements. We have a moment of inertia of 200 inch to the 4th. Okay. And so this moment of inertia will apply to elements A and C, okay, which are our 2 vertical elements. Okay, and we have a second moment of inertia of 100 inch to the 4th, and this is going to apply only to element B. All right. And so with this geometry and with these properties, what we're interested in is computing the displacements and rotations at every node. All right, so what we have is a a fairly standard finite element problem, and so we've tackled problems like this before. Of course, the only wrinkle here is that we have frame elements instead of trusses or beams, and so that's going to present some it's not going to change our process, and so we're still going to follow the same steps in our solution, but it will involve a lot more math than usual, compared to our previous ones. And of course, nodes 1 and 4 are fixed, just for the sake of completeness. Okay. And so that can save us some time, once we go to apply our boundary conditions and assemble. Okay, any questions on the problem setup? Okay. All right, so let's go ahead and start chunking through this problem. Okay? And so just like we always do for these kinds of problems, we're starting with our element stiffness matrices. Okay. Then we'll start with element A. And so element A, you can see element A is pointed vertically up. Okay. And since node 1 is on the bottom and node 2 is up top, in order to get to this configuration, we had to rotate by an angle of 90 degrees. Okay. And I said I would use phi, but I didn't use it here. Okay, so for element A, phi is equal to 90 degrees. Okay. And of course, cosine of 90 is equal to 0, and sine of 90 is equal to 1. Okay. All right. And so that helps us out a lot. And so basically any cosine term or any term with cosine in our frame element stiffness matrix, we can just get rid of it because it's just going to be multiplied by 0. Okay. And so what can also help is if you compute some of the coefficients in the matrix. Okay. And so sub coefficients that show up pretty commonly are 12i over L squared. Okay. Right. And so if you look at our frame element stiffness matrix, that quantity there shows up quite a lot. And so it kind of helps to kind of pre-compute this. Okay. And so if we plug in the numbers for this, we end up with 0.167 inch square. We also have 6i over L, right? So this shows up quite a lot in the element stiffness matrix. And so let's go ahead and pre-compute it. So we can just go ahead and plug it in. And so if we plug in the numbers for this, we get 10 inch cube, okay? And the last thing I'm going to compute here is E over L, which is the value of the coefficient in front of the matrix. Okay. Right, and so the value for this is 250,000 pound per inch cube. All right. And so with all that in mind, we are ready to compute the element stiffness matrix for element A. Okay. And so this is a lot of plugging and chugging, but we can go ahead and do it. And so we're basically going to plug into everything here, keeping in mind that everything with a cosine is just going to go to 0. Okay. All right. So let's go ahead and start writing it out. So element A here is connected to nodes 1 and 2, and so we're going to have F1x, F1y, M1, F2x, F2y, M2. Okay. This is going to be equal to, you have 250,000 out in front. Right, and then we can start plugging in numbers. So let me go ahead and write out the first row first. Okay, so we have 0.167, and we have 0, so we have minus 10, minus 0.167, 0, minus 10. Okay. Then we have 10, 0, 0, minus 10, 0. Okay. Then we have 800, 10, 0, 400. We have 0.167, 0, 10. Okay. And we have 10, 0, 800. And of course, this element stiffness matrix is symmetric. And so I'm going to go ahead and write in the symmetric parts now. Okay. Right, and so the full thing has the following values. Okay. And so again, for this problem, we saved a lot of time just because our angle here was 90, and so everything with the cosine we just kind of ignored. Okay. All right. Any questions on how we obtain this here? Yeah.
Which form of the stiffness matrix did you use there?
I used this one up here.
The big one we just did?
Yeah. Yeah. Mm-hmm. Okay, so that's element A. I think we have enough time for element B. We might get through element C as well. Okay. And so for element B, the orientation angle here is 0 degrees, okay, because it's a horizontal element. Okay. So if cosine of 0 is 1 and sine of 0 is 0. Okay. And so, very similarly, we have something that's going to save us a lot of work because, a lot of the terms are just going to go out to 0. Okay. And just like I did for element A, I'm going to compute the terms here. Okay. The ones that show up most often. And so we have 12I over L squared. We plug in the numbers for this, we get 0.0835 inch square. Okay. We have 6I over L, this is equal to 5.0 inch cube. Okay. And our E over L here is still the same. So we have 250,000 pounds per inch cube. Okay, so let's go ahead and start plugging this in. And I think that'll be the last thing that we do today. All right, element B. So element B here is connected to nodes 2 and 3. And so we have an F2x, F2y, theta 2, F3x, F3y, theta 3. Okay. This is equal to 250,000. Okay. Oh, sorry. Yeah, it's M2, M3. Thank you for that. Okay, so let's go ahead and start filling this in. So we have a 10, we have a 0, 0, minus 10, 0, 0. Okay. The third row and the last row are always the easiest, just because they don't involve too many terms. Okay. Now, if we multiply this by the displacements, we have u2x, u2y, u2, u3x, u3y, and theta 3. Okay. Okay. So yeah, it's you know, we've done a lot of calculations already, but we're still only just getting started with this example. Okay. And so that's kind of as far as I want to get to today. And so of course, we have element C, but we'll do that next week. Okay. All right, questions. So before the end of class, can I discuss problem 1C? Yes. Oh, yes, for sure. Yeah. I think that might be covered later in this notes, but I can cover it very quickly at the end of lecture today. Yeah. And so the question was if I can go over problem 1C on the homework just kind of really briefly, because I think the formal discussion for is at the end of this set of lecture notes, but we can talk about it really quick. It's pretty easy to do. Okay. But let me just hang on here for just one more minute in case people need to write it down, or is everyone good on this right now? Okay. All right, so let me go ahead and stop sharing. Let me come to this one now. Okay. Okay, and so we have homework 2 here, beam and frame problems. Okay. Okay, so problem 1C. So problem 1C asks you to explain what happens for when you have both a Dirichlet and Neumann boundary condition applied at the same point. Okay. And so what that basically means that if you have, say in this problem right here where node 1 is fixed, what happens if we were to apply a force on here at the same time? Right. And so basically what happens is that, you don't apply both at the same time. The only one that you apply is the Dirichlet boundary condition. And so the Dirichlet, whenever you have two, both a load and a constraint applied at the same time, then the constraint is always going to take precedence. Okay. And so you only apply this one. Okay. And so you don't bother applying the Neumann boundary condition. And so you only apply the fixed support basically. Okay. And so, physically, if you think about it, if a structure is fixed at a certain point and you try to push it at that fixed constraint, nothing's going to happen, right? And so because the structure is fixed there, and so you have to reflect that as well with the boundary conditions. Okay. And so the other thing I said, before we go, and so now that you know stuff about frames, and if I told you that this right here is a frame problem, you'll probably start cursing my name. And so, just like I said before, this problem right here is optional now. Because how many elements we have here? 1, 2, 3, 4, 5, 6. Yeah, 6 frame elements. That's cruel. That's cruel and unusual for even for my standards. And so you don't have to do this problem. And so for yeah, and a lot of them are angled as well. And so it's and they're not even 45-degree angles. They're 60 and 30. So so please don't do this one. I mean, you're free to do it, of course. I'm not going to stop you, but to get credit, you don't have to do that one. Yeah. All right. Any final questions before we wrap it up for today? Okay. All right. So thank you guys for coming today. I know it was a shortened week, and so I appreciate you guys coming out. So definitely get started on the next homework because even without that last one, it's still quite a doozy, and so there's quite a bit of work to it. So hope you guys have a great weekend, and I'll see you guys on Monday. Yep. Tomorrow they're 1 to 2 o'clock. Yep.
I kept getting on the last 3 homework problems. I know for sure where I got 3B wrong. I accidentally used the wrong index. And then I realized right after I finished because I went back to double check it. And I was like, why did I get that wrong? And I realized I should use -45 and -60 originally. And I didn't do that. And I was like, okay, there's no way I'm gonna redo this entire. It took me like an hour and 20 minutes to do it.
These are very time consuming. Yeah.
I was like, yeah, I'm not gonna do it again. So I just noted it on for 2A and 2 or and 4 for 3A and 4, so 3A after the fact, I double checked my or triple checked my work, and I could not find my mistake. And then problem 4, I like double checked at every step, and still ended up with the wrong answer. And I'm not exactly sure why.
Okay.
But,
Yeah, let's talk in office hours tomorrow, and then
yeah,
I can
it's
look
gonna
through
take
your
way
work.
too long to go through it right now.
Yeah. Let's talk in office hours tomorrow.
All right, sounds good.
All right, Rafael, any final questions before we wrap it up for the week? Okay, all right, so I'm gonna go ahead and close the Zoom call. So have a great weekend.